And you'll notice that if you look at charts on the National Weather Service website, sometimes you'll look at it and you'll compare the line that they drew to the actual reading, and you'll say, that doesn't look quite right.
Okay, we're back with the second part of our ground school tonight, talking about aviation weather. If you enjoyed the first part, we'll build off of that and get a little bit more deeper dive into what's going on. Thanks everybody for watching. We appreciate all the comments and likes that we get. Please remember to like and subscribe and leave a comment. I love it when you leave comments on Facebook when I post these videos, but if you leave them on my YouTube video as well, I don't care if they're the same. That helps the rankings and stuff, and the likes all help with the YouTube rankings to get us up there, get some more eyeballs on our videos, and hopefully some more subscriptions, so we can bring this journey and this message to more people, which is what we're trying to do. Thanks for watching. Remember to do all that stuff at the bottom, and if for some reason I trim any of this particular lesson out, you can watch them minus my silliness at the beginning and the end on Jake's channel at Flying Fiddler CFI. I got the name right this time. I usually call it Jake. Anyway, you can see it all in its entirety at Jake's channel, Flying Fiddler CFI, and do some extra learning that way. So let's get rolling here and dive into the next part of weather.
Okay, so let's pick up where we left off. We were talking about how the air movement from high pressure to low pressure areas gets bent around by Coriolis force into a circular pattern as it moves from the equator towards the pole, getting bent to the east, and from the pole towards the equator, getting bent to the west. So as that happens, on figure 6-3 here, you can see a low pressure system here, which they have at 989 millibars in this case, and a high pressure system at 1019 millibars. So neither of these is very energetic. The high is not very high and the low is not very low, but you have, you'll notice this essentially looks like a topographic map of ground. Mm-hmm. So, and that's in a sense basically what it is, because you're measuring highs and lows of atmospheric pressure. So in a sense, you can think of the high pressure, which is the blue dot there in figure 6-3, as sort of a hill, and the red dot is sort of a valley, and the lines in between them as contour lines. And what those contour lines are is obviously where the pressure is all the same. So 989 in the center there of the low, then pressure goes up to 992, and everywhere along that line is 992. And the next line is 996, then 1000. So you'll notice that they have little dots all over the place here to simulate measurement points or barometers on the ground. If you just draw a line from one point to the next, connect all the ones that say 1000, you'll get the line for 1000.
Why do we have 1000 intersecting with our 996s?
Well, the graphing isn't perfect, and you'll see this if you look at action.
Really should go somewhere like this.
Yeah, something like that.
You can't see that, but I drew a line in there and flattened it out a little bit.
Yep. And you'll notice that if you look at charts on the National Weather Service website, sometimes you'll look at it and you'll compare the line that they drew to the actual reading, and you'll say, that doesn't look quite right. It happens. But in any case, as we measure the pressure, you get these lines where the pressure is all the same, and that sort of gives us that topographic map almost of where the higher pressure is and where the lower pressure is. These lines are called isobars. ISO, again, as we talked about in the last session at one point, ISO means the same, and bar in this case is a measurement of atmosphere. So we talk about pressure in millibars. 1 bar is 1,000 millibars, which is roughly a standard atmosphere.
So if the lines were closer together between the two, it's going to be windier. So you can follow those lines and see where the winds will increase or decrease to plan your route around it.
That's, as the lines get closer together, that means that the temperature is changing faster as you move across them.
Which means it's going
right,
or the other way.
Now, we also talked about how as the air flows outward from a high, it gets bent around. If it flows north, it gets bent around to the east. If it flows south, it gets bent around to the west, and we talked about why that happens. But we also talked about how it'll continue to get bent around until the Coriolis force is equal, causing it to bend, is equal to the pressure gradient force pulling it in the direction of the high or low pressure that it wants to go. In this case, towards low pressure if it's flowing outward from a high. And when those two are in equilibrium, the pressure gradient force with the Coriolis force, the air will be traveling in a stable direction. You'll find that that direction is traveling pretty much along these isobars, or these lines of constant pressure. So the wind will sort of spiral outward from a high, following those lines, and then eventually it'll pick up on one of the lines that's halfway in between. It'll start spiraling in towards the low pressure system. So in figure 6-3 here, if the air travels north, it'll get bent around to the east, and eventually it'll get to the halfway point, and then it'll want to travel towards the low, but it'll get bent around to the west as it travels south then, and you'll end up with air starting out traveling north away from the high, gets bent around all the way around until it's traveling south, and then it spirals in.
It's picked up by the low because it's moving toward the low, so it gets picked up in those.
Yep, and then it spirals in towards the low.
This wind is, say, 5 degrees, 5 miles an hour going this way. It has to find a low pressure wind more than 5 miles an hour before it'll get picked up. Because otherwise, wouldn't the 5 mile an hour versus a 3 mile an hour, wouldn't it just keep going with its 5 mile an hour channel? I don't know. It's something that just hit me.
It doesn't quite work that way. I mean, it's the wind will always follow those isobars, and then it'll essentially spiral. It has more to do with how high the high is and how low the low is.
How big the difference
so
is.
If it'll spiral outwards until it gets to the point that's halfway in between the two pressures.
So if these were bigger, it would probably change directions higher up, farther up towards north for it.
Yeah,
because they're closer together.
You could think about it that way. Yeah, okay. that would work. Here in figure 6-2, they show how lows, highs are typically depicted. They also show a trough and a ridge. So a trough is essentially a low pressure system that's not just a point, but it's an elongated area of low pressure, and a ridge is the opposite. It's a high that's essentially been stretched out or elongated. But in talking about air pressure and areas of higher pressure and lower pressure, trough is an elongated lower pressure, and ridge is an elongated area of higher pressure. So here, in figure 6-4, they show a high, but then also area of pressure leading away from the high that's also remaining high in pressure. So that would be a high pressure ridge, and the same thing for a low pressure trough. And typically, you can see how the isobars deflect around that down to the south for the low pressure system. That might be something that would cause a dip in the jet stream as well. So that's part of the reason why you might hear those terms used to mean slightly different things interchangeably because they are connected, as that shows, but you're referring to slightly different phenomenon. Now, something to talk about as we get into how this affects weather systems in general. So as the air circulates around a high pressure system or a low pressure system,
Is that the one we were looking at before?
7-9 I believe is the
7-9.
one we had up before, how the arrows spiral inwards towards the low and outwards away from the high. So you'll notice the low pressure system they depict here over the Midwest is probably going to pick up warm, moist air from
Off
over
the
the Gulf of Mexico, and it's going to bring it up through Tennessee, Kentucky, into Ohio, Indiana, and bend it around through Michigan into Wisconsin. And the high pressure system out west is going to pick up air. It's going to pick up some air from the Pacific coast, which is going to be moist but cooler than the air from the Gulf of Mexico, but it's also going to pick up air from the Canadian prairies, which is very cold and dry. So as you have air circulation around a high or a low, it's not just the air sort of orbiting around it, but it's also picking up moisture and temperature characteristics from the ground underneath it. And as you pick up heat or moisture from a warmer area of ocean or land, you have a warmer, what they call an air mass, or an area of air that's traveling around or rotating around that low pressure or high pressure system. So particularly in the case of a low, if we look at in this case, you'll pick up warm, moist air from the Gulf of Mexico here, which is going to come north up into the Midwest. And as it does that, it's going to encounter air that's cooler and drier because it's been sitting over land, and the warm air will tend to push out the cold air, but it'll do it because warm air is less dense and it tends to rise. The warm air will kind of ride up over the top of the colder air, and you'll have this sort of very gradual transition from the warm air coming up over the cold air. Now, skipping pages a little bit here to continue talking, we've talked a little bit about air masses here, about picking up the characteristics of the ground or the ocean underneath it. So air masses are referred to by two different words, and there are it's a two-part name. So you can have refers to temperature and moisture. So in terms of temperature, you can have Arctic, polar, or tropical. So Arctic obviously is the coldest air. Polar is air from around, the mid-latitudes, from around, anywhere from central Canada down into as far south as about Madison here. And then tropical will be a warmer air from down, Gulf of Mexico down south of there. Moisture, you can have continental, which is air that has been sitting over land and is drier, or you can have maritime, which is air that's been sitting over
the ocean.
The ocean has picked up more water. So this can give us 5 different possible kinds of air masses. Continental Arctic, which is cold and dry. Continental polar, which is cold and dry, but not quite as cold. Continental tropical, which is hot and dry. Maritime polar, or maritime tropical. You can possibly have maritime Arctic, but you really don't see those around this
Because
part
the
of the
really
world
cold
very
doesn't
much.
hold much water, right?
It doesn't hold much water, and also there's, because of the way the land is distributed around the high Arctic, air that you get coming through this part of the world won't have had enough time over water if it's in the Arctic to take on those properties. Over in Northern Europe, you might be a little more likely to see a maritime Arctic air mass than you would be in North America, just because of the way the land is distributed up north. But as we talked about back in 7-9, so the air that's getting picked up from the Gulf of Mexico then would obviously be a maritime tropical air mass. It's warm and wet, and that's getting pulled up into the Midwest. And then the air that's coming down from Canada would be a continental polar air mass. So if we look at that low pressure system, you have the warm, moist air, the maritime tropical air mass coming up to the north along the east side of this low here and displacing a continental polar air mass, which is cooler and drier. But then you also have a continental polar air mass coming down from Canada being drawn around the west side of the low pressure system, around the south side of it, and cold air typically will move faster, and since it's more dense, it'll typically displace warmer air faster than the other way around. Because if you look at the way one air mass moves into another, and looking on figure 10-5 here, when cold air comes in to displace warm air, the cold air is more dense and it tends to sink more, so it comes in underneath the warm air mass and pushes it out of the way, sort of from the bottom up. Whereas if you have a warm air mass moving into a cold air mass, since the warm air mass is less dense, lighter, it tends to move up over top of the cold air and not displace it as quickly, because it'll just flow up over the top rather than getting in underneath it. And if you have cold air moving into an area of warm air and displacing it, this is called a cold front. If you have warm air moving into an area of cold air and slowly displacing it, that would be a warm front. So because the cold front, in this case in figure 10-5, comes in, the air comes in underneath the warm air, it'll tend to push it upwards. Now the warm air already probably has moisture in it, so when that air gets lifted, we already talked about how that happens with thermal. The air gets lifted up, and it'll expand it'll cool, and at a certain point it will reach its saturation point and form clouds and eventually rain. And because the cold air is pushing in underneath the warm air, that front edge of that cold air that's pushing in underneath sort of gets blunted, and it just, because it has to push that warm air up and out of the way. And you can see that in figure 10-5, where the boundary sort of gets
it's not gradual.
Not gradual. It gets to be rather sudden at the surface. Whereas if you look in figure 10-6 with the warm air, it's a much gentler slope, and as the warm air gets pushed up by the cold air coming in underneath it, with that sort of sharp angle, it'll tend to get lifted more rapidly, which can cause more severe weather, because the faster you lift the air, the more energy it has when it hits that point where the temperature and dew point collide, which causes
So in the middle of summer, when it's really ugly, we have to go to our basement.
that's
It's
typically
because, and it makes sense because once that storm passes, you go outside and it's like a breath of fresh air. It's nice and cool.
exactly.
But it's a violent
Yep.
pounding to get in there.
Right, and it'll typically be a fairly narrow band.
Yeah,
like
it's
that
over
because
just like 5 minutes. It's
right,
boom, it hits you. And
because that leading edge of the cold air is steep enough that once it's passed, versus when a warm front comes through, you see how the warm air kind of rides up over the cold air much more gently, and that causes a much wider area of.
That's when we have all day rain.
That's when we have those soakers.
Yep.
Wider area of precipitation, because it's lifting the air over a wider area, but it's lifting it less violently, so you'll get less severe weather but more spread out.
Right.
And so planning a flight as a pilot, if we have to go across a cold front, we can expect that there's going to be a wind shift, obviously, but we can also expect that there's going to be a more localized area of clouds and possibly precipitation, possibly thunderstorms, whereas if we're flying across a warm front, it's going to be more spread out. Furthermore, if you're ahead of a warm front, so you see in figure 10-6 here how the front is moving from left to right of this picture.
Mm-hmm.
So we're at the right edge of the picture, and we have to fly to the left edge of this picture from the cold area into the warm area. You'll notice that at the right edge, those clouds are fairly thin and fairly high.
Mm-hmm.
Okay? As we get further and further towards where the warm front is at the surface, the clouds start coming down further and further. We get more rain, which is probably going to reduce visibility. So if you're flying towards an advancing warm front, you can expect that you'll encounter clouds which will get progressively lower and lower, and visibility which will deteriorate, and you'll probably encounter IFR conditions, which for a VFR private pilot is not somewhere you want to be.
No.
So crossing each kind of front has its hazards, but at least with a cold front, because it's more localized, the weather in those small areas may be more violent, but it's also typically easier to see and avoid.
Because you'll see it.
You'll
and
see
you can
it.
Fly around it, or
Either fly around it or have more warning to, land and wait till it passes. Whereas if you're flying towards a warm front, it's more likely to sucker you in, because it's going to be getting worse and worse, but
Yep.
gradually.
Yep, your ceilings are
And
decreasing.
your ceilings are coming down. Now you're in what we call scud running, staying just below the clouds, trying to stay in VFR conditions. As you get closer and closer to the warm front, those clouds are going to keep coming down and down and down. And if you don't have a good idea of what to expect as you get close to a warm front like that, you can find yourself surprised by the clouds coming down and possibly some drizzle starting, the visibility getting worse. So that's part of the reason it's important to know the structure of a front and what to expect. Now, we've talked about highs and lows and how the low particularly picks up different air masses and those rotate around it. So there's a series of figures here, starting with figure 10-9. So the way that the low pressure, the rotation of the low pressure system gets started is you'll have a cold air mass and a warm air mass, and wind flowing one way on one side and the other way on the other side. Anytime you have two masses of air flowing in opposite directions, you get what's called a shear, where essentially the air has friction with other air. And as it has friction, it'll get slowed down at that boundary. If you have air that's moving faster away from that boundary, and it gets slowed down. If you get close to the boundary, well, you have air moving in one direction here, and the opposite direction here, and it gets slower and slower as it gets to the center. Well, now you've got a perfect condition set up to get sort of a rotation, and that's in figure 10-10. You start to see a rotation develop because of that friction of the air with itself, and as it rotates around, you start to get that low pressure center.
Is that how a tornado starts?
Not a tornado so much as just a low pressure system. This is over the, a tornado is maybe...
This is on a bigger scale.
Yeah, this is much bigger scale. I mean,
States-
tornadoes do get started that same way, but on a very
micro scale.
tiny scale. A scale of maybe a mile or two. We're talking about a scale here of,
multiple states.
3 or 4 states. Yeah.
Okay.
But you get that rotation, and then you start to get that, which is helped along by the Coriolis effect, as we talked about earlier, wind getting bent around to the east as it flows north and to the west as it flows south. And you start to get this rotation, and as the air picks up characteristics, the air coming down from the north will tend to pick up cooler and drier characteristics. The air coming up from the south will pick up warmer and wetter characteristics, and you start to develop this very characteristic pattern, which is sometimes called the standard model of a low pressure system. Another name for it is the Norwegian polar frontal model, because it was developed by meteorologists in Norway during the First World War as they were trying to forecast weather. And this is part of the reason why we call the boundary between two air masses a front, because these Norwegian meteorologists back in about 100 years ago, a little over 100 years ago, were looking at the weather, trying to, they didn't have satellite photos and all the kind of network of sensors that we have today.
Yeah.
They were trying to figure this stuff out from pretty rudimentary means. And as they began to get a picture of what we've been talking about here, about the air masses and how they rotate around pressure centers, they realized that you have one air mass displacing another, as we just talked about a minute ago. And when you have one mass of something displacing another mass of something, well, World War I was going on around them, so they called it a front, because that's what they were that's what they were thinking about at the time. So a little bit of tangent there about the history of it, but in any case, you get this very characteristic pattern. So in figure 10-11 here, you see that cold front coming down from the top left or from the northwest, displacing the warmer, wetter air to the south, but also as the low rotates, you get the warmer, moister air with a warm front coming up to the north and east and displacing the cooler air in that direction. And as you get this circulation, you begin to develop this very characteristic pattern. And as you look at weather charts every day, start to look at
when they put them in motion, you can see those.
Exactly, and you'll start to see a very characteristic kind of structure developing here. They're all going to look fairly similar. And if we think about what we talked about how the warm front is very gradual. It has ahead of it you have clouds which slowly get lower and lower and lower as you get towards the warm front, as it moves towards you. That is that area of green shown here in figure 10-11. That would be as it gets darker and darker green, that would be the clouds that get lower and lower and more widespread precipitation. Whereas the cold front lifts the air more violently, and you have a narrower band of precipitation at or just behind the cold front as that air gets lifted you'll get more thunder, cumulonimbus clouds, which we can talk about later, but sort of the puffy clouds, tall clouds. You'll get area of more intense rain, possibly thunderstorms because of that vertical air movement, air moving up and down next to each other at high speeds. Instead of having, we talked about that shear zone with air moving across the surface leading to how a low forms in the first place, you can also have friction between air that's moving up and air that's moving down. So as air gets lifted by a cold front, it'll get lifted very rapidly, but then it'll spread out at some point and it'll start falling again. And the division point between where that air is being lifted and where it starts to fall down again, you get air that's moving up on one side and down on the other. You get a lot of air with having friction with itself, and friction creates static electricity, and that's, you get
thunderstorms,
lightning and thunder. But interestingly enough, the lightning and thunder itself is not what's the most dangerous to airplanes, because if an airplane gets hit by lightning, well, in the case of the Chief, it's a big steel cage around us, and you might know that as a Faraday cage, where it will very effectively take the electricity and round it around us, and will protect us from.
But we're not going to test that, are we?
We're not going to test that.
Don't want to.
It will route lightning around us, so it's not actually the lightning which is the most dangerous to us, although it's the movement of air, because the rising air and falling air, to get enough of a shear zone there between the rising and falling air to create a static discharge in the form of lightning, you're talking about air that's moving up at maybe 10 to 15,000 feet a minute. Now in the Chief we climb at about 500 feet a minute. So you got air that's moving up at maybe 10,000 feet a minute on one side and air that's moving down at 10,000 feet a minute on the other side.
And that's what makes the rumble of a thunder, just like rubbing.
No, the rumble
Oh,
of
the light, that's the lightning.
The lightning heating up the air essentially creates a shock wave or an explosion when the air heats up due to the static discharge. But in this case, the rising and falling air, if you fly from air that's going down at 15,000 feet a minute into air that's going up at 15,000 feet a minute,
can rip you in half.
Just think of how many G's you're going to pull. That's what's the most dangerous to us as pilots about thunderstorms. Is not actually the thunder and lightning. The thunder and lightning is actually kind of useful because it tells us where that rapid air movement is happening. If you see flashes of lightning, you can assume that there's going to be air moving up very quickly and air moving down very quickly right next to each other. And that's what's making.
But if you get out from that, it's much calmer.
To get back to the overall macro structure of the low pressure system, you get thunderstorms forming along that cold front as the air gets lifted, and that's why you get what we call a squall line, which is a line of very intense thunderstorms that's moving across the ground, all as a unit. A squall line will typically be along a cold front, and that'll be an area of very intense lifting of the air, which causes very intense rain because it hits that dew point wall with a lot of energy, and it also creates lightning and thunder because of the rapid moving air against each other, creating static electricity. Now, we talked a little bit about how the cold front will typically travel faster than the warm front because it's more dense, moving faster. So in figure 10-12 here, you see that eventually the cold front begins to catch up with the warm front here at the center, and then that proceeds outward along the fronts. And as that happens, you get what's called an occluded front, where a cold front has overtaken the warm front. And then you just get basically a confused mess. You get an occluded front has some of the characteristics of both a cold front and a warm front.
You don't want to be there with a plane, right?
Yeah, because in this case, the cold, dry air is overtaking the warm, moist air, which is in the process of overtaking the cool, damp air, and you just get a very confused mess. So you might get, you probably won't get a very intense squall line, but you may get the kind of thunderstorms you would associate with a cold front. You'll probably see those. You may also, though, see the kind of widespread precipitation and low clouds that you would associate with a warm front. So you'll see some of the bad stuff associated with each. And as that proceeds along into figure 10-13 here, you can see that eventually the cold front will sort of absorb the warm front, but as that happens, it'll lose energy because the cold front and the warm front will eventually sort of cancel each other out. And as that happens, the whole low pressure system will start to dissipate and sort of spin itself into just...
So that's how they go away.
That's how they go away.
Interesting.
So you get the entire life cycle here of a low pressure system from figure 10-9 all the way to figure 10-13 here, starting with that shear zone of air moving one way and the other, which will start the rotation of the low pressure system, which will wrap up and eventually cause cold front and a warm front to start rotating around them. The cold front will eventually catch up with the warm front and dissipate it, and then the whole low pressure system will dissipate as that happens.
That's how it all works.
Yep. And that gets us basically to the end of chapter 10. So that's...
All right. Well, thanks a lot, Jake.
Yeah.
I hope you learned something. That chapter was kind of fascinating because it's like I see some of this in the news. I see it on the weather. Oh, I saw Weather Junkie.
Yep.
And she often gets the forecast better than they do just by looking at their radars. But that's a different story. Anyway, it was fun. Hope you learned something. If you learned something, leave a comment down there and tell us what you learned. That way we will respond to it. If you have a question, leave a question down in the comments of the video, and who knows, maybe I'll know the answer. I'll answer it. If not, I'll ask Jake to answer it. And maybe we can help you out and maybe find something that we would want to cover in a future lesson when we talk about weather, if you bring up a good question. So leave us some comments down there. Remember to subscribe. And if you like all this and you just want the learning and not my silliness, subscribe to Jake's channel, Flying Fiddler CFI, and you can learn lots more fun stuff. So I guess that will wrap up for today, and we will see you next time when, I'm not sure what we're covering next. Is it more weather? We dropped our syllabus on the floor.
Yep, next time we'll be continuing on with weather, so
we'll dive into some crazy stuff.
Get through most of the rest of aviation weather here.
Okay. So will be more chances to make your brain hurt and to get more questions answered. And once we're done, we can go to TV station and be a meteorologist, right? Not quite, but those guys I can't imagine what their college must be like. They're training for this because it's so so variable and
you
so
get
many...
you get into a lot more of how to predict weather, how to make computer models that accurately simulate all the stuff we started talking about. I mean, we're talking at the very basic level about...
And my brain hurts at the basic level. I can't imagine what a meteorologist goes through when they're in school.
Yeah.
So anyway, thanks for watching, and we will see you next time.